Okay, good afternoon, children. So now we are going to start with group 18 elements. Okay, that's the last group that comes under the P block. Okay, group 18. Their common name is noble gases or inert gases. Okay, their common name is noble gases or inert gases. So these are group 18 elements. These are the last group in the periodic table and P block. So these are the elements present in group 18. They are known as noble gases or inert gases. Okay. And helium, then neon, argon, krypton, xenon, radon, then organozone. Okay, organozone. So these are the elements present in group 18. We know that the configuration of helium, that is 1s2. Okay, 1s2. And in the case of all other elements, they have 8 electrons in their outermost shell. In the case of helium, only 2 electrons in the outermost shell. Then all other elements have 8 electrons in their outermost shell. Clear, children? Okay, then this radon, that's a radioactive element. And this organozone, it's a symbol with OG and its atomic number is 118. It can also prepared synthetically. Okay, it's a synthetically radioactive element, organozone. So these are the basic things about group 18. Then we are moving to each specific properties. Okay. So which are the elements present in group 18? Aditya, can you please read the names of the elements? Group 18.
Helium, neon, argon, krypton, xenon, radon, organozone.
Okay, organozone. So next about their occurrence. Okay, occurrence of these metals. So all these gases except radon and organozone, they are occurring in nature itself. All other noble gases except radon and organozone, it can occur in nature itself. Then this helium and neon, they are found in the minerals of radioactive origin. Okay, helium and neon, they are found in minerals of radioactive origin. Example, pitch blende, then monazite, clevettite. These are the ores of different metals. Okay, so along with this ores, the sources of helium and neon also present there. That means helium and neon is present in small amount in the ores of different metals. Clear, children? Examples are pitch blende, monazite, cleveite, etc. And in the case of helium, the main source of helium, that is natural gas itself. Okay, main source of helium, that is natural gas itself. Then the xenon and radon, they are the rarest elements of the group. They are found in very rare from nature. Xenon and radon. And the radon is obtained as a decay product of radium. Okay, you can see the reaction. On decaying this radium, radon will be obtained along with helium. Okay, this radon and helium will be obtained from this decaying of radium. This one is radium, Ra. It will be converted to radon, Rn for radon. So radon is obtained as decay product of radium. And in the textbook, there is one reaction related to the origin of organozone. I told you it's a synthetically radioactive element. It can be produced by collision of CF atoms and I think CF, it's just 1 minute, children. CF for calcium and CF. Yeah, californium. Okay, CF is californium. So the collision between californium and calcium, this organozone will be produced. So these are the occurrence of different metals, different elements present in group 18, noble gases. First one about all the gases except radon and organozone, it will present in nature itself. Then this helium and neon are found in the minerals of radioactive origin, that is pitch blende, then monazite, clevite, etc. Then the helium main source is natural gas. Okay. Then the xenon and radon are rarest elements. Radon can be obtained by the radioactive decay of radium, and organozone will be obtained from californium and calcium collision. So that's about the occurrence of this metal elements in the group 18. Then similarly, we have learned the examples that comes in the last member of this group, livermorium, moscovium, etc. Here in the case of organozone also, the complete properties are not yet studied because only small amount of element will be obtained through this synthetic production. Okay. So we are discussing the properties of remaining elements. Their general configuration is NS2, NP6, except helium. We know that helium, its configuration is 1s2, right? Then the general configuration is ns2, np6 for remaining elements in the group, and are noble gases because they generally do not interact with most of the elements. They do not take part in chemical reactions because they are already stable. They have a completely filled configuration. Clear, children? They have a completely filled configuration. That means 8 electrons present in their outermost shell. Say they do not take part in chemical reactions. Okay. Then due to their stable configuration, they have very high ionization enthalpy. They are already stable, right? They are already stable. But in the case of other elements, they take part in chemical reaction to attain stability. So in the case of this noble gases or inert gases, they are already stable. So high ionization enthalpy is required to break the bond between the atoms or to remove the electron from the outermost shell. Ionization enthalpy, that's the energy required to remove the electron from the outermost shell, right? So here in the case of this noble gases, they are already stable. Okay, so it is very difficult to remove one electron from its outermost shell and it will become unstable. That's why here high ionization enthalpy for this noble gases or inert gases. Clear? That's about their ionization enthalpy, and the atomic radii, it will increases down the group. Okay, atomic radii, it will increases down the group from top to bottom. That's same in all p block elements, right? When the atomic number increases, their size also increases in a group from top to bottom. Then next one is electron gain enthalpy. Here in the case of electron gain enthalpy, usually the value of electron gain enthalpy is negative, right? Highly negative for this group 17, isn't it? Group 17, they are highly negative electron gain enthalpy. But in the case of this group 18, normally we have learned that this ionization enthalpy, electron gain enthalpy increases from left to right. But in the case of noble gases, it's an exception. It has a high positive value of electron gain enthalpy because they do not want any other electron to make the outermost shell complete. They are already stable. So they have a positive value of electron gain enthalpy. Clear, children? They have a positive value of electron gain enthalpy. So these are the basic properties. Electronic configuration NS2, NP6 except helium. Then ionization enthalpy, high value of ionization enthalpy. Then atomic radii, it will increases from top to bottom. Then electron gain enthalpy, high positive value of electron gain enthalpy. They are already stable. They do not want any other electron to complete its outermost shell. Okay. So that's about the basic thing. Then we are moving to the physical properties. Okay. Physical properties. Here they are monoatomic, not monotonic. Okay, monoatomic. Monoatomic means only one atom, right? They can exist in independent state or free state. Okay, but in the case of all other elements, hydrogen, then oxygen, nitrogen, chlorine, etc., they will always combine with same atom to form a molecule in nature. They cannot exist in free state. But in the case of noble gases, they are already stable. So they can exist as a monoatomic molecule. Monoatomic means only one atom is present. Okay. Then they are colorless and sparingly soluble in water. They are monoatomic, colorless, and sparingly soluble in water. They are tasteless too. Okay, no characteristic taste, then colorless, sparingly soluble in water. Then they have low melting and boiling points because of only type of interatomic interaction in this elements is weak dispersion forces. So the force exists between this atom, that is weak dispersion forces. So they have very low melting point and boiling point. On a small heating itself, it will be converted to vapor or it's melted. Okay, because the force of attraction between these atoms, it's very weak. It's a weak dispersion force. Weak dispersion force exists between the interatomic interaction. So it has a very low melting point and boiling point. On small heating, it will be converted to vapor or it starts to melt. Clear, children? Okay, then the last point, helium. It has the lowest boiling point of 4.2 Kelvin. Okay, it has the lowest boiling point of 4.2 Kelvin and has an unusual property of diffusing through most commonly used gas materials like rubber, glass, or plastic. This helium has very low boiling point, 4.2 Kelvin, and has an unusual property of diffusing. What is diffusion? Movement from higher concentration to lower concentration, right? So here the molecules of helium gas, it will move from higher concentration of helium to lower concentration of helium in commonly used gas materials like rubber, glass, or plastics. Okay. Gas materials like rubber, glass, or plastics. So these are the certain physical properties of group 18. They are known as noble gases or inert gases. This is clear? Yes. Then we are moving to chemical properties. Michael, have you completed?
Yes, ma'am.
Okay, okay. Then next one about the chemical properties. We usually learn that in the case of this noble gases, they do not take part in chemical reactions, right? They do not take part in chemical reactions. They are stable. They do not react with other chemicals to form compounds, isn't it? But here, there are two reasons for their less reaction compared to other elements. Okay, the first one is that the noble gases except helium have completely filled ns2 np6 electronic configuration in their valence shell. We know that they have a completely filled outermost shell, right? So no need to accept or donate electrons. So they do not take part in chemical reaction. That's the first reason. And the second one, they have high ionization enthalpy and more positive electron gain enthalpy. They have high ionization enthalpy and positive electron gain enthalpy. Okay, positive electron gain enthalpy. So due to these two reasons, normally these noble gases do not take part in chemical reaction. Okay, that's a common thing. But here there are certain exceptions, and the reaction, chemical reactivity of this group 18 elements, it was discovered by a scientist through this activity. Okay, so Neil Bartlett, that's the name of the scientist. He prepared a red compound which is formulated as O2 plus PT F6 minus. Okay, he prepared a red colored compound using oxygen, platinum, and fluorine. He then realized that the first ionization enthalpy of molecular oxygen, that is 1175 kilojoule per mole. Okay, he used oxygen, platinum, and fluorine. Okay, and he find that the ionization enthalpy, the energy required to remove the electron from their outermost shell, that is nearly 1175 kilojoule per mole. And it is almost identical with that of xenon. Okay, xenon is the element that belongs to group 18 and its value is 1170 kilojoule per mole. Then he made efforts to prepare same type of compound with xenon instead of oxygen. Here you can see oxygen, platinum and fluorine, right? And when he checked the ionization enthalpy of oxygen, it is nearly equal to xenon. So instead of oxygen, he is trying to prepare a compound using xenon. And he made efforts to prepare same type of compound with xenon and was successful in preparing another red colored compound, Xc plus PtF6 minus. So instead of oxygen, here it is xenon. By mixing platinum F6, PtF6 and xenon. Clear, children? First, he prepared a red compound and the main elements present is oxygen, platinum and fluorine. Okay. Then later, instead of oxygen, he used xenon because their ionization enthalpy almost same. And he succeeded in that experiment. And later we can learn that, or we can conclude that this certain elements present in group 18, they can react with other elements to form compounds. So this is considered as the beginning of the study of certain group 18 elements and their chemical reactions. Clear? Then the xenon forms mainly 3 fluorides under 3 specific conditions. So the xenon is reactive. It can react with other elements to form compounds. And here you can see it will prepare or it can make 3 fluorides under 3 specific conditions. Here the reagents are same, but the conditions are different. Okay, reagents are same, but the conditions are different. In the first case, xenon and fluorine will react together and xenon in excess. Xenon in excess and the temperature is 673 Kelvin and 1 bar pressure. Okay, and XeF2 is formed. XeF2 is formed. Clear, children? The next one, Xc plus fluorine itself. Here the ratio is 1:5. Ratio is 1:5 and here the product is XeF4. The change in temperature and pressure. Temperature is 873 Kelvin and the pressure is 7 bar. And the last one, xenon and fluorine itself, the ratio is 1:20. Then the product formed is XeF6. And here also the change in temperature and pressure, 573 Kelvin, then 60 to 70 bar atmospheric pressure. So depending upon specific conditions, the product obtained will be different. The same reagents are used, xenon and fluorine. Okay, but the specific conditions for each chemical reaction, it will be different. So depending upon their conditions, different products will be obtained. Clear? This is clear, children? Yes or no?
Yes, ma'am.
Yes, okay. Then the next compound, that is using this XeF4 and O2F2. Another method of preparation of XeF6. Here you can see the third reaction that related to the formation of XeF6, right? XeF6. So these all compounds are known as xenon fluorine compounds. Okay. Xenon fluorine compounds because xenon and fluorine combine together to form compounds. So this XeF6, it can be prepared by another method of preparation. XeF4 plus O2F2 give XeF6 plus O2. Interaction of XeF4 and O2F2. And here the temperature is 143 Kelvin. 143 Kelvin. Then these three are XeF2, then XeF4, XeF6, xenon fluorine compounds. They are colorless crystalline solids and sublime readily at 298 Kelvin. What's the meaning of sublime? They can be directly converted to the form of vapors. Okay, so these are certain properties Colorless crystalline solids. These three are colorless crystalline solids. Okay, colorless crystalline solids. Then they are sublime in nature. They can be directly converted to the form of vapors. From solid state, they will directly convert it to vapors. Okay, and they are powerful fluorinating agents. They are powerful fluorinating agents. They can supply fluorine to other elements or compounds. Fluorinating agents. Okay, they are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents and they are readily hydrolyzed even by the traces of water. I'll share the next slide, then we can discuss. Yeah, they are powerful fluorinating agents and are readily hydrolyzed by water. Hydrolyzed means water can be added to that compound. Here you can see the reaction XCF2. Okay, XCF2 plus 2H2O gives 2Xc plus 4HF plus O2. So they are powerful fluorinating agents and are readily hydrolyzed by water. And here that's the reaction related to this one. This property XCF2 plus H2O gives 2Xc plus 4HF plus O2. And the next one about the structures of each this compound. We have learned 3 xenon fluorine compounds, XCF2, XCF4, XEF6. Then each compound have their own characteristic structure related to VSEPR theory, valence shell electron repulsion theory. Okay, in the case of XCF2, it has a linear structure. XCF2, it has a linear structure. Then XCF4, it has a square planar structure. It has a square planar structure. Then XCF6, it has a distorted octahedral structure. Distorted octahedral structure. Okay, these all structure related to their valence shell electron pair repulsion theory, that is VSEPR theory. Clear, children? Aditya, can you read the structures of these compounds? Xenon fluorine compounds.
Yes, ma'am. XCF2 linear.
Yeah.
Xenon XCF4 square planar. XCF6 distorted octahedral.
Okay, distorted octahedral. Then another reaction, the xenon fluorides react with fluorides to form cationic species and fluoroanions. Okay, this is another reaction with the xenon fluorides, that is XCF2, XCF4 and XCF6. That is xenon fluorides react with fluorides to form cationic species and fluoroanions. Cationic species means they will convert it to plus form. That means positive charge. And in the case of fluoro, that will be converted to anion, negative charge. Clear, children? Look at the reaction. Here this one is an xenon fluoride, right? Xenon fluoride, which will react with another fluoride, that is PF5. Then this xenon fluoride, it will be converted to cationic species. And this fluoride, it will be converted to anionic species. Positive charge with this one and the negative charge with fluoroanion. Okay, then look at the another reaction, XCF4 plus SBF5. Here also xenon fluoride react with another fluoride. Then the product formed will be XEF3. Okay, XEF3. It has a positive charge. It's that exists as cationic species, and the fluoride part that will exist as anionic species. The third example, XCF6 plus MF. Here also, the xenon fluoride will react with another fluoride, and M plus then XCF7 minus will be formed. And the last one, there is a change in the reaction, right? Okay, normally this xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. Okay, that's a common thing. This xenon fluoride will be converted to cationic part, and this remaining fluorine part that will be converted to anionic part. Clear, children? This is clear? Yes, right? Okay. Then the last one, that's hydrolysis of XCF4 and XCF6. Hydrolysis of XCF4 and XCF6. They are known as xenon oxygen compounds. Here, xenon oxygen compounds will be obtained. Oxygen compounds will be obtained as the product. Xenon fluoride react with oxygen to form xenon oxygen compound. Xenon oxygen compounds. The first reaction, XCF4 plus H2O. It will react with H2O. Sorry, not oxygen, H2O. Hydrolysis, right? Plus H2O. XCF4 plus H2O gives Xc, then XCO3 plus HF plus O2. So xenon oxygen compound will be obtained when they are reacting with water molecule. Hydrolysis of XCF4. The next one is XCF6. Here also the same xenon oxygen compound will be produced. That's the hydrolysis of XCF4 and XCF6. They are known as xenon fluorine compounds. Then the last one, partial hydrolysis of XCF6. Partial hydrolysis. XCF6 plus H2O gives XeOF4. XeOF4. They are known as oxyfluorides. Okay, oxyfluorides. On complete hydrolysis, xenon oxygen compounds will be produced, that is XeO3. Okay, and on partial hydrolysis, oxyfluorides will be obtained. XeOF4, then XeO2F2. They are known as oxyfluorides. Oxyfluorides. XeOF4, XeO2F2. Both are oxyfluorides. Here this XeO3, that is xenon oxygen compound. On complete hydrolysis, xenon oxygen compound. On partial hydrolysis, oxyfluoride will be obtained. All of you, please switch on your videos. Vidur, can you tell me which product will be obtained when xenon fluoride will be react with water on complete hydrolysis?
Oxyfluorides.
Complete hydrolysis, not partial.
XeO.
That is known as xenon oxygen compound. Okay, XeO3, right? XeO3. That is xenon oxygen compound or xenon oxide. And on partial hydrolysis, oxyfluoride will be obtained. Oxyfluoride. There are two forms, XeOF4, then XeO2F2. Okay. Then this XeO3 is a colorless explosive solid with pyramidal structure, and XeF4 is a, here it is XeOF4. XeOF4, that is oxyfluoride. This one is XeO3, that is oxygen, xenon oxygen compound. That is a colorless explosive solid with pyramidal structure. Okay, the pyramidal structure. And XeOF4, it's a colorless volatile liquid with square pyramidal structure. with a square pyramidal structure. This one is XeO3. Here you can see pyramidal structure, and this one is XeOF4, square pyramidal structure. And this linear, square planar, and distorted octahedral, that's related to XeF2, XeF4, XeF6. So its structures are very important. Okay, XeF2 it's linear, XeF4 it's square planar, XeF4 distorted octahedral, then XeOF4 square pyramidal, XeO3 pyramidal structure. Clear, children? So that's about the important compounds formed by the reaction of noble gas or inert gas like xenon with oxygen and fluorine. Okay. XeF2 that is linear, XeF4 square planar, here it is XeF6 distorted octahedral, then XeOF4 square pyramidal, XeO3 it's pyramidal. So it's clear?
Ma'am,
Yeah.
we have to learn this like this figures and also the reaction, right?
Yeah, figures also. Sometimes figures can be shown and you have to select the correct option. Definitely in the case of oxo acids. Okay. I told you about the structure in oxo acids, right? So oxo acid, you should learn the structure. Okay. I will check about this one. At least you have to learn the name of that structure for this one. Okay. Linear, square planar, distorted octahedral, square pyramidal, and pyramidal. Clear? So that's about this chapter. Then last thing, uses. Uses of noble gases or inert gases. All of you please switch on your videos. Nandana, can you read the uses of helium?
Helium is a non-inflammable and light gas. Hence, it is used in filling balloons for meteorological observations.
Yeah.
It is also used in gas-cooled nuclear reactors. Liquid helium with a boiling point of 4.2 Kelvin finds use as a cryogenic agent for carrying out various experiments at low temperatures. It is used to produce and sustain powerful superconducting magnets, which form an essential part of modern NMR spectrometers and magnetic resonance imaging systems for clinical diagnosis. It is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood.
Okay, that's enough. So in the case of helium, there are many uses. It's a non-inflammable gas. That means flames are not produced on its burning. Okay, and it's a light gas that is used in filling balloons. Then for meteorological observations, then it is used in gas-cooled nuclear reactors. Then this liquid helium, it is used as a cryogenic agent. Cryogenic agent means the reaction that take place in or the process that take place in very low temperature. Okay. So here it is used as a reagent for using in very low temperature, that is known as cryogenic agent. Okay, cryogenic agent. Then related to deep freezing. Okay, deep freezing, that's at very low temperature, right? So this helium can be used as a cryogenic agent. Then it is used to produce and sustain powerful superconducting magnets. It is in NMR spectrometer, then MRI system for clinical diagnosis. For this purposes, this helium is used. Then it is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood. So that's about the uses of this helium. Gayatri, can you please read the uses of neon?
Neon is used in discharge tubes and fluorescent bulbs for advertisement display purposes. Neon bulbs are used in botanical gardens and greenhouses.
Okay. So in the case of neon, it is used in discharge tube and fluorescent bulbs. Okay, so the gas present in discharge tube and fluorescent bulbs, that is neon. Then it will bulbs for their advertisement display purposes. This neon gases used to fill the discharge tube and fluorescent bulb. And this neon bulbs are used in botanical gardens and in greenhouses. Okay. Then about argon. Nevin, can you read the uses of argon? Nevin, can you hear me?
What did you say? Ma'am keeps on cutting.
Uses of argon. Page number 211.
Used while welding.
Starting like this, argon is used mainly to provide an inert atmosphere. Yeah, arc welding, that same thing. Network issue there. Anna, can you read?
Yes, ma'am.
Yes.
Argon is used mainly to provide an inert atmosphere in high temperature metallurgical processes, arc welding of metals or alloys, and filling electric bulbs.
Okay.
It is also used in the laboratory for handling substances that are air sensitive.
Okay. Sometimes, okay, that's enough. Sometimes inert atmosphere is needed. What is inert atmosphere? That means prevention of further chemical reaction. So for providing such inert atmosphere, this argon is used mainly in high temperature, mainly for metallurgical purposes or processes. What is this metallurgical processes? That is the extraction of pure form of metal from its ore. Okay, so such processes are take place in inert atmosphere. So this argon will provide inert atmosphere for such processes and for filling electric bulbs. Okay, for filling electric bulbs, this argon is used. Then it is used in laboratory for handling substances that are air sensitive. And this argon is used in laboratory for handling substances that are air sensitive. Okay, even they are sensitive to air. In such cases, we will use this argon. So it will prevent the reaction with air. Then last one, there are no significant uses of xenon and krypton. They are used in light bulbs designed for special purposes. So no need to learn the uses of xenon and krypton. Okay. So now we have completed this chapter. It's a very big chapter, I know that. And I'm going very fastly through this chapter. Then during our revision days, we can learn it well. Okay. So for next Thursday, there is only one period, right? So you should revise this portion about group 15 elements. Okay, group 15 elements. So group 15 elements, their occurrence, electronic configuration, atomic and ionic radii, ionization enthalpy, electronegativity, physical properties, chemical properties. Chemical properties including oxidation state. Then anomalous properties of nitrogen. Then their chemical reactions. Dinitrogen. Then ammonia. Nitric acid. Okay. Yeah, these are the portions that belongs to group 50. The case of ammonia, nitric acid and dinitrogen, their preparation, properties and uses. So all of you read this portion very well for the next class. Then we can discuss the MCQ questions related to this portion. Okay. Then when you read this chapter, this portion, if you have any doubt in any point, you can ask me. Clear? Is clear, children? Okay.
Yes,
Then let me take your attendance. Just wait. Okay, children. Then I will share the slides of today's topic. Okay. Then thank you all. See you in the next class. Bye.
Thank you.
Thank you.